Hey Sid, so I made you a video yesterday talking about the two different forms of radioactive decay. 7th period hasn't quite gotten to them yet, totally because of all the interruptions that we've had from the career day and other things like that with band and choir. So you're pretty much caught up. The last video I made you was about alpha decay, and all I said, the main thing in that was, look, when an atom is unstable, one of the ways it can decay is by emitting something called an alpha particle. And if you remember from the last video, that just consists of 2 protons and 2 neutrons. Okay, and so because of that, when you have one atom that decays into another thing, and you've changed the number of protons, you've completely changed it all. And so every single time when something decays in alpha decay, it loses 2 protons and loses a mass of 4. Okay, so that was just one of the forms. All right, so I'm going to go to another. And so the other one is, instead of alpha, another thing that it can do, another way it can decay, is through something called beta decay. So there's alpha and beta decay. Beta decay is a little different, but it's the same principle in the sense that it changes into something else. So you have your atom, right? And then in the middle you have your nucleus, and it's still full of protons and neutrons and whatnot. The only difference this time is, unlike alpha decay, beta decay doesn't necessarily, it does emit something, but what it does is a little bit different. The tenet behind beta decay is that one of its neutrons literally changes into a proton. So one of its neutrons changes into a proton. Okay, and in doing so, it emits something called a beta particle. And to sort of give you a description of what a beta particle is, I can kind of do this. I can say, if this circle right here represents a neutron, and this circle right here represents a proton, and then I'll have just kind of a measly little electron hanging out over here. What happens from start to finish is that the neutron turns into a proton, and in doing so, you've now created this proton from the neutron, and in doing so, you emit this electron. And this electron is the thing that's known as a beta particle. So all a beta particle is just a really fast-moving electron. Fast-moving electron. Okay, but the main thing here to understand is that if I can highlight this real quick, the neutron turns into a proton, and at the same time you kind of emit an electron from the atom itself. Okay, so what are the effects of that? Well, when you do that, you can see, if I just have an example real quick, if I do something like carbon-14, there's a 6 right here. If something like carbon-14 goes through beta decay, if you remember from the last video, this number right here tells you the number of protons, and this number right here tells you, it's the mass number, and it tells you the number of protons plus neutrons. And so if carbon-14 goes through beta decay, and that means one of its neutrons turns into a proton, that means it's essentially gained 1 proton. And so because of that, you can, this number right here has to change. And so what we can do is, instead of it being 6, it's now 7. And a lot of people right away, they want to change this number to 15, right? But if you remember this, like I said earlier, it's just the sum of your neutrons and protons. And so if one of your neutrons just turned into a proton, you didn't change any mass, it just turned into something else. And so the number actually stays the same. So the mass stays the same. But because the number of protons changed, it's a completely different element. And in order to figure out which element it is, you just have to look at your periodic table. And if you look at the periodic table, the element that has an atomic number of 6 is carbon. The element that has the atomic number of 7 is nitrogen. Okay. Okay, and so it's literally changed its identity. And in addition to writing the new element, you have to kind of just like we did for alpha decay, you have to symbolize to the reader that it's gone through beta decay. And the way you do that is you write a Greek letter beta, or the symbol for beta, which is just kind of like, it looks kind of like a cursive capital B, I guess. And how you signify that is with a -1 right here and then a 0 up here. The -1 indicates the beta particle. So if you remember in the last slide, that was just the electron that got shot out. It's really fast moving, and electrons have a negative charge. That's the -1 part. And then electrons are so tiny that their mass is basically negligible. It's so close to 0. It's very tiny. So we just say 0 instead of some complicated number. And so this whole thing is a nuclear equation that would explain beta decay. Okay, so I'm going to write this problem right here. This would be like a problem I would give in class where I say iodine 131, and there's atomic number 53. Iodine 131 decays into something, right? And the decay that it has is beta decay. And so you would be responsible for telling me what's supposed to go in this question mark. And the exact opposite could happen too. I could start with this, I could have something in place of this question mark in the beta, and then you'd have to work backwards and tell me what it was. One thing I didn't mention in the last video was that the names of what it was before and after are different as well. Not just what they are as elements, but we give them specific names. And so this is called the parent atom, and then this one would be called the daughter. Okay, and that sort of makes sense because this atom came from this atom, and so whatever this is right here with this question mark will be the daughter of this parent. So why don't you take a second to write that down, solve it for yourself, and pretty much as far as Wednesday is concerned, you're pretty much caught up. I'll do another video on nuclear half-life and nuclear calculations, but at least you're pretty much caught up, so by the time you get back, you won't be in the dark.